Thanks for joining me for the beginning of section 3.4 on tangent planes, differentials, and differentiability. The goal of this section is to develop a geometric understanding of tangent planes and differentiability, and to use linearizations and differentials to approximate function values. We'll begin the section by reviewing differentiability for a function of a single variable. A function f of x is called differentiable if at x equals a, the derivative limit f prime of a, which is the limit as h goes to 0 of f of a plus h minus f of a over h exists. F has a well-defined tangent line at a exactly when f is differentiable at a. When f is differentiable at a, the following is true in a small interval around a. The tangent line and the function share only one point, called the point of tangency. The tangent line is a good approximation for the function, and the function's graph is connected and smooth, which means that there are no discontinuities or sharp points. So we would like to capture this kind of situation for functions of several variables. For functions of two variables, for example, we'd like to have the concept of not a tangent line, but a tangent plane to the graph of a function f of xy at a point AB, and we would like it to have similar characteristics to those we've listed above. Defining differentiability is a little trickier with more variables, however, because there is not just a single derivative limit. We will begin, therefore, with a more geometric approach to tangent planes and leave the discussion of differentiability until the end of the section. We are going to use the word differentiable before the end of the section, however. When we call a function f of xy differentiable, we will mean that its surface represents the graph of a function that is smooth and connected, and that the tangent plane is well defined and is a good approximation for f at all points in the function's domain. Definition 3.4.1. Let P with coordinates ABC be a point on a surface S, and let C be any curve lying entirely on S and passing through P. If all the tangent lines to all the possible curves C can be contained within a common plane, we call this plane the tangent plane to S at P. For example, if we were to imagine a surface and some points AB with image potentially, if this is a function at a point P, with ABC, so that C is f of AB. Now this definition is valid for surfaces that are not functions, but the function is the graph that I have drawn here. We're imagining all sorts of curves drawn on that function surface passing through the point P. All of those curves have tangent lines defined. We saw those in our unit on vector curves. If we are able to contain all of those tangent lines in a single common plane, that plane is called the tangent plane. And that is the graphical representation of it. The tangent plane is to a surface as a tangent line is to a curve. Locally, it will share only the point of tangency with the surface, in a diagram point P. And near the point of tangency, the tangent plane will match the surface, the shape of the surface, very well. In the next video, we will see a geometric derivation for the equation of the tangent plane for a function f of xy.